So we will now move to the next speaker, but we will also present results for the steel industry from the INSPIREWATER project. So the speaker is Andreas Rosberg from Sandvik. Sandvik is a global engineering group for mining and metal manufacturing. So yes, he will present innovative and sustainable solution, and more specifically for the recovery of acids. So Andreas, can you hear me? Are you ready to
present?
Yes, I
can hear you. Can you hear me?
Okay, perfect.
Yes, we can.
Okay, great. It works.
So you can take the lead on the presentation. Maybe press the next slide.
Yeah. So this project was about recovery of acids at Sandvik Materials Technology in Sandviken, Sweden. Go to the next slide. So the background that we use pickling baths for pickling of high alloy tubes, which we are producing here in Sandviken. And for one of the pickling processes, we are using mixture of phosphoric and sulfuric acid that has a lifespan which is limited by the metal content in the acid. So basically, we have to replace it in a certain amount of time. We also, to clean the tubes afterwards, we use rinsing in tap water, which are used 3 different baths, and these are, of course, also changed regularly. The waste management consists of, pickling acid is going to landfill. We can't reuse that any way, so it goes to Norway. The rinse water is pumped to our wastewater treatment plant and handled there. So that was the background to why we wanted to do this project. So the goal and purpose of this project was to demonstrate the recovery of phosphoric and sulfuric acid from the pickling acid we use, and also to demonstrate the rinse water recovery, basically to have a zero liquid discharge, so a closed loop with the wastewater. We also wanted to see the long-term behavior of the process, since this would, of course, be used in the process and recirculate both water and acid. Next slide. So an overview of the present situation, where we have the pickling baths, which are actually several pickling baths, with the acid going in and spent acid going to landfill. We have 4 different baths, whereof 3 are used in water, potable water going in. The first one is, of course, the major amount of water going in there. And that one is going to the wastewater treatment plant. We have such a plant in our industrial area, where it is treated there and goes into the cooling pond. Okay. So that was the present situation. The INSPIREWATER solution to in this project was to have a solution for the pickling baths and acid, consisting of chromium-6 reduction, since we need to reduce the chromium-6. There was a microfiltration. In between, there was actually another filtration. There is a nanofiltration, where the actual recovery of acid is taking place, and the outcome from this would be spent acid, and also acid going into the evaporation to correct the amount of acid and water in the fluid, and that will then go back to the pickling bath. The other solution for the wastewater was to have the water going from the different baths into a reverse osmosis equipment, and then the water will go back into the baths. Some water will also go back to the pickling baths. Some ideas about the nanofiltration. This is just a very short, brief picture, but what we do is that we need to do the reduction, as I told you about. We have the pre-filtration to reduce particles, and nanofiltration, which is taking place like this, where the metal is kept on one side of the filter, and the phosphorus and sulfuric acid is going through. So high metal retention and low phosphorus retention on the nanofiltration was basics. Going into results, we used the AMS 3012 membrane. We used it at I would say up to 70 bar and also 40 degrees. So it showed good amount of recovery, up to 75%. We showed also that concentration of acid was one very important factor in this, and the dilution was a way to increase the yield. So basically we could start with the filtration with concentrated acid and then improve the yield by adding water, basically to increase the yield of the nanofiltration. Of course, that would end up with a more diluted acid, which meant we had to use more evaporation, and sort of gave a balance to energy versus the yield. We also did the trials with rinse water recovery, which is basically using a reverse osmosis to filtrate the water from the phosphorus acid. So also in this case we needed to do a reduction of the chromium 6 to have the filters to basically increase the lifespan of the filters. We also had the pre-filtration of this. This technology seemed to work very well, so we could have very high metal retention and high phosphorus retention, so quite successful. The results, the LCA results showed that, well, basically this was used, what we see is calculated on 20% reduced acid consumption. And what we showed later in the project was that we could come up to 52% of reduced consumption. So the 20% was actually what we aimed for, and we see good LCA results, but it could be improved even further. Yeah, next LCA results showed here. Also the same thing, calculated on 20% reduced phosphoric acid consumption. So that will of course be increased further if we come up to 52%. LCC results shows, first picture is showed pickling acid recovery only, and the second is pickling acid and rinse water recovery combination. Rinse water is, we have plenty of water in Sandvik and as in all steel industry in Sweden, so it's not a big cost issue, but we are looking at using less and less water anyway. So I would say it doesn't show that well in the LCC, but it will be beneficial to reduce the amount of water. So summary, and the picture actually show it's a bit hard to see, but over back here is the pilot actually for the nanofiltration. So we think that we had a successful process for the recovery of acids. We could see that we could save over 50% of the acid, which of course decrease the amount of landfill that we have to do, and the acid is also very costly. Both the landfill and the new buying new acid is very costly, so you could see very nice cost reduction if this could be implemented. Reduction of water was almost closed loop. Don't remember the percentage, but it was very close to 100%, I would say. So it looks very possible and very good. Of course, the cost reductions isn't that good since water is very cheap here. So, but it's possible, and it would be if we want to reduce the amount of water we use in the rinsing bath, that would be a technical possible solution. We're looking at the continue the project, so well, basically we will start to look at how to implement, at least for the both methods actually. So it will be interesting to see if we can have this in place in sometimes in the future. Oh, sorry.
All good.
The last pictures I had to show you. So
yes. So
okay,
Eric, there you are. Okay.
Yes, thank you very much, Andreas, for this presentation. I see that we have only one question from the audience, so I think, well, maybe you should take coffees, because there is a question about the lifetime decrease that is due to the exposure of the membranes to acids. You have some data on this? Can you answer this question? Andreas?
Lifetime of the filters.
Yes, of the filters. Or the membrane filters also.
Yeah, let's see if Fredrik could assist me in this one. I know we had some issues with the reverse osmosis in that filter, that we actually had some issues with the life of the filter. So Nanofiltration, we could see only a small degradation, so it seems to work, but for the reverse osmosis we have an issue with acidious water.
Yeah.
So it could be sort of a problem in the future going full scale.
Yes, Fredrik, you want to add something?
Yeah, I would like to add that for the nanofiltration membranes, we only use these acid stable membranes from AMS, and we also tried the Suez Duracid membrane, and we didn't see any degradation in any of those. But like Andreas said, for the reverse osmosis, a little bit like Martin said before, there's a lot of different waters, rinse waters in this case, and some are more concentrated, and when some more concentrated rinse waters enter the reverse osmosis slope, we had some issues.
Okay. I have another question related to the cost saving associated with the water treatment and reuse. Okay, you mentioned the cost reduction for saving phosphoric acid or landfill, discard to landfill. How does it compare with the cost of water itself? Is it much higher? Or the reduction of water saving?
Can you repeat that?
Yes, I mean, it seems that the saving, the cost saving associated to this is not really related to the water cost itself, is it? Or it's more related with the phosphoric acid? I think you presented this in the LCC.
Yeah. The cost savings of recovery of the acid is, of course, very large. So in compared to that, the cost for the water is very small, of course, and actually it depends a bit on how you look at it also. We're sort of not really having more or less any cost of the water actually, but we still have a limit on the amount of water we can use in our plant, so there is still some kind of cost. So it's a bit difficult to calculate, I would say, how much cost we would spend on reducing the amount of water we use. So we usually use other KPIs on water consumption at our site, while phosphoric acid is, of course, a bill that has to be paid, so that's actual true cost saving.
Okay.